Hey folks. So I want to do a few more examples solving improper integrals. I picked two integrals from the book. One is type 1, one is type 2. I haven't worked through them completely, so we're going to do this in real time. So this first integral is an integral from negative infinity to 0. So this is type 1. Let's go ahead and set this up. So that's going to be a limit as n approaches negative infinity of the integral of n to 0. Okay, my function is z e to the 2z dz. Now to solve this integral, this is set up very nicely for a integration by parts. So I'm going to let u be z, dv be e to the 2z dz, and then du is dz, and v is 1/2 e to the 2z. Okay, so now carry my limit with me. This integral can be written as uv, so 1/2 z e to the 2z, minus integral v to u, so that's minus 1/2 e to the 2z dz. Okay, and I'll just carry along to remind myself I'm going from z equals n up to 0. Okay, so now what do I get? This is the limit as n approaches negative infinity. I need to complete my integration, so I'm going to copy down 1/2 z e to the 2z minus now integrate e to the 2z. That's another half in front, so it's minus 1/4 e to the 2z evaluated from n up to 0. Okay, let's go ahead and evaluate by plugging in our bounds. So if I plug in 0 first, I'm getting, well, 0 minus plug in, so minus 1/4 times e to the 0 is 1. So that's, okay, plugging in 0. Minus, let's plug in n. So this is 1/2 n e to the 2n minus 1/4 e to the 2n. Okay, so now I've plugged in my 0 and my n. And let's go ahead, let's simplify this a bit. So this should be equal to, I can pull the negative 1/4 out, right? That's being added to the front here now. I have the limit as n approaches negative infinity of, let's see. So this is negative 1/2 n e to the 2n, and then distribute that minus sign, so be plus 1/4 e to the 2n. Okay. So now, first things first, I notice this 1/4 e to the 2n. As n goes to negative infinity, this is e to the minus infinity. This is going to 0, right? I'm remembering my graph of e to the x. And so as I approach negative infinity, e to the minus infinity is going to be 0. And so what I need to do is calculate this part. So the limit as n goes to minus infinity of n e to the 2n. Okay, now here's what I'm noticing. So if I were to try to plug in negative infinity to this, I'm going to get, okay, the minus 1/2 doesn't really matter so much, but it's going to be negative infinity times e to the minus infinity, which really means I'm getting something like negative infinity times 0. Now, this is indeterminate, right? So I actually don't have an answer for this yet. So what I need to do is evaluate this limit using L'Hopital's rule. Okay. So what should I do? Maybe I should do this as sort of a side problem. So maybe on the side of my page, I'll sort of set up what is the limit as n approaches negative infinity of, I can ignore the negative 1/2 and leave it for the n. So I'm just going to calculate n e to the 2n. Okay. And so because this looked like a negative infinity times 0, what I should do is rewrite this as a fraction. So this is going to be the limit as n approaches negative infinity of n over e to the minus 2n. Okay, so I brought the exponential function to the denominator, but added a minus sign to the exponent. And so now when I plug in infinity here, or negative infinity, I'm going to get negative infinity on the top, and then e to the negative to negative infinity. So that's going to be plus infinity, right? So that's e to the plus infinity, which, yeah, is plus infinity, right? So now this is perfectly set up for L'Hopital. And so I could evaluate this as the limit as n approaches negative infinity. Now let's take a derivative of the top. So derivative of, n is just 1. And then derivative of the bottom, so that's e to the minus 2n times negative 2. And now as I plug in more and more negative numbers, they're getting greater in absolute value. So what's happening now is I'm getting basically 1 over negative 2 e to the plus infinity, right? So it's, again, negative 2 times negative infinity. It's going to be plus infinity. So I'm getting 1 over humongous numbers, humongous negative numbers, fine. But at the end of the day, that's going to be 0 overall for my limit. So, okay, what does that tell me? Going back to my original problem, that tells me that this limit is actually 0. And so all the limits go away. What I'm left with is just negative a fourth plus zeros, and that's my final answer, negative a fourth. Okay. Okay. Question number 2. Here's another integral. This looks like a normal integral. At least it has finite bounds. But I do notice that my integrand has a discontinuity at x equals 1, and that is inside this interval. Okay, so this is a type 2 improper integral. So I'm noticing that x equals 1 is a discontinuity. And so to solve this integral, I actually need to set up sort of my two smaller integrals. Um, okay, so this needs to be broken up into two pieces. I need to first integrate from 0 up to some n. Let me give myself a little bit more room. And then let n get closer to 1 from the left, sorry. Okay, so I'm going to approach 1 upward, okay? And then I have my integral here. Plus, then I need to solve separately this limit as n approaches 1 from the right. And now I'm going to do what? From n up to 9. Here's my function. Okay. And as always, if you're not sure about this, you can always draw a picture, a sketch to try to help remember what's happening here. So what's happening in this function, I have something that looks like this. It's going down. If I plug in bigger numbers, it's going up like this maybe. I don't know, it should be positive, I suppose. So maybe it looks like this. Okay. So whatever, we have a plot that looks like this. Here's my 9, here's my 0, discontinuity at 1. And I'm trying to calculate the area under this curve. So what I'm going to do is say, let's integrate first from 0 up to an n. That's going to get close to 1. And then I'm going to integrate from another n up to 9. And then let that go back to 1 from the right. Okay, and then try to calculate these two areas. If both of these areas make sense in the limit, then I can add those two numbers together. That's going to be my answer. So let's see if this works. Okay, in either case, I need to go ahead and calculate the antiderivative of 1 over the cube root of x minus 1. Okay, so let's start with the first one. Limit as n approaches 1 from the left. And so, you know what might help, by the way? Maybe I write this as x minus 1 to the negative 1/3, yeah, rather than 1 over cube root. And so this will help me see that I can use, okay, properly you could use a u sub, but because this is just x minus 1 on the inside, I know u sub will work really nicely. There's no sort of extra factors. So I can go ahead and just get the antiderivative as x minus 1 to the, so I need to add 1, right? So there's going to be 2/3, and then divided by 2/3 is the same as 3/2. Okay, so 3/2. So that's my antiderivative. I'm going to plug in 0 and n. Wonderful. Plus, okay, you could do this first one all by itself if you'd like. I'm just going to write down both because it's the same antiderivative, right, both times. So this is going to be 3/2 x minus 1 to the 2/3. And then this again, I'm going to plug in starting at n and then go up to 9. Okay, cool. Um, let's see, what happens if I plug in my numbers here? So as I plug in n approaches 1 from the left. Okay, so I'm going to start by plugging in n here. So this is 3 over 2, n minus 1 to the 2/3, minus, go ahead and plug in 0. So that's 3 over 2, and then negative 1 to the 2/3. plus the limit as n approaches 1 from the right. Same game. Let me go ahead, plug in 9 first. That's going to be 9 minus 1 is 8 to the 2/3 minus 3 halves. And now n minus 1 to the 2/3. Okay. So I sure hope both of these limit problems work. There's a lot of work for something if it doesn't work. Let's see. So in this first, actually, no, at the point I can just kind of try to plug in. So if I try to evaluate this limit as n approaches 1, I can just plug in 1 for n, right? I'm going to get 1 minus 1 is 0. And 0 to the 2/3 is 0, and then that's okay. And then 0 times 3 halves is 0. So this actually just evaluates by plugging in n equals 1. This is a continuous function. There's actually no problem plugging in 1 identically. So this limit works. It's just 0 minus, and then I see here I'm going to get 3 halves, and then -1 squared is 1, cube root is still 1. Okay, so this is going to be 3 halves times 1. And then plus, and I bet something similar is going to happen here. So 3 halves times, okay, 8 to the 2/3. So it's cube root of 8 is 2, squared is 4, so it's going to be 4, minus, and again, I can evaluate this limit by just plugging in here, n equals 1. It's going to give me 3 halves, and then 1 times 1 is 0 to the 2/3. And there's no problems here. I don't need to use any special machinery. This evaluates by continuity, just by plugging in 1 to get the limit. So this is great. This is just 0. And so both of these limits worked out. So because the first limit evaluated to a number, the second one evaluated to a number, this integral must be convergent, and I can get an actual answer here. So let's just combine our answers. This is minus 3 halves plus 12 halves, which gives us 9 halves overall. That's the area under the curve. It worked. All right. Hopefully this was helpful. Let me know if you have any questions.